Hey everyone, welcome into this next lecture video on indeterminate forms. In this video we're going to compute some limits, and we will use L'Hopital's rule as we are able to, so as necessary. So let's just get right into it. First of all, we want to try to compute this limit as x approaches infinity of x times sine of pi over x. When we do this, we can kind of break it up into parts here, and so the limit as x approaches infinity of x times the limit as x approaches infinity of sine of pi over x. This becomes infinity, obviously, times this limit can go inside because sine is a continuous function. So limit as x approaches infinity, pi over x. And so this becomes infinity times sine of 0, or infinity times 0. And this is an indeterminate form because in a limit, right, we never actually get where we're going. So what does this mean? This means that this is a really big number times a really little number. So which one rules, right? Does it get really big? Does it get really small? Which one's happening faster in some sense? So indeterminate means we cannot determine what the limit is, right? So this is indeterminate. Now, we want to try to apply L'Hopital's rule to this, but right now, the way it looks right now, L'Hopital's rule does not apply. Okay, because L'Hopital's rule only applies, I'm sure you remember, to limits that are indeterminate of the form 0 over 0 or some flavor of infinity over infinity. So these are the two indeterminate forms for which L'Hopital's rule does apply. This is not one of them. So our first step is to try to modify this limit just by doing algebra, not by changing anything, so that it becomes one of these two. And the obvious thing to do here is to think of x as 1 over x. All right, it's kind of a weird thing to do, but the reciprocal of a reciprocal, right, cancel out. And as long as x is not 0, which it's a very large number, it's away from 0, then this is perfectly fine. And we can do this. And then what we'll do is just think of this one as being underneath this, right? So again, haven't changed anything here, but we are going to interpret this limit now as the limit of sine of pi over x over 1 over x. And now when we apply the limits to each one of these, I'm not going to work through all the details again, but the same thing happens, right? We end up with 0 over 0 this time, and now L'Hopital applies, right? Now L'Hopital applies. And remember, L'Hopital tells us, what L'Hopital's rule tells us, that if this limit exists, right, then it's going to be equal to the limit as x approaches infinity. So I'm going to put a little LH right here for L'Hopital. So L'Hopital's rule says, right, that limit, if it exists, is equal to the limit of the ratio of the derivative. So I'm going to write this out in a couple steps since this is our first example video. So sine of pi over x prime over 1 over x prime. And when we do this, let's see what happens. This is the limit as x approaches infinity of derivative of sine is cosine. So that's cosine of pi over x times the derivative of the inside. So that's pi over x prime over 1 over x prime, right? And pi over x prime, pi is a constant. So I'm leaving this in kind of a wacky way here because look what's going to happen. Limit as x approaches infinity. This is now going to, the pi comes out of the derivative, but we're left with a 1 over x prime times cosine of pi over x, all divided by the derivative 1 over x prime. And the reason I've left it this way, now maybe you can see it, is that these two are the same, right? Now we know what this is, so we could work this out. I'll write it up here. We know that 1 over x prime is negative 1 over x squared, right? And so the point is that this is a legitimate function as long as x is away from 0, which again it is. But in a limit, we are allowed to cancel like terms always, right? So these two can be canceled out from our limit without even computing it. I mean, I computed it up here, but we don't need to, right? Just by very carefully applying the chain rule to the top and then noticing that we get out this term that's the same as the bottom. Our limit now becomes simply the limit as x approaches infinity of pi times cosine of pi over x. All right? Again, everything here is continuous, so this becomes pi times cosine of 0, right? The limit of the inside is 0, and cosine of 0 is 1. So this is just pi. All right? So this tells us that the limit as x approaches infinity of x times sine of pi over x is equal to pi. So let me write down the conclusion there. limit as x approaches infinity of x times sine of pi over x is equal to pi. All right. Now, on to the next one. Let's see what we've got. This one wants us to compute the limit of x minus the natural log of x as x approaches infinity. So again, the first thing that we do is kind of distribute this out and see if it's even indeterminate at all to begin with, right? And so we plug in limit as x approaches infinity of x is, of course, infinity, minus the limit as x approaches infinity of log of x, which is also infinity. And so this says infinity minus infinity, which, you know, if infinity was a number, this would be 0. But actually what this says is really big minus really big. But really big is a relative term, right? It just means that this number is eventually going to infinity. It's possible that this really big could be smaller than this really big, or bigger than this really big, or whatever, right? So they could be related somehow, and so this is indeterminate. This could be 0, it could be 1, it could be anything, right? So it's indeterminate. The question mark there is not whether it's it is indeterminate, okay? The reason the question mark was there is because we don't know what this equals. So now, if we want to try to compute this, we need to get this into the form of L'Hopital's rule, right? We cannot apply L'Hopital's rule to this difference. We need a 0 over 0 or infinity over infinity again. So for this one way to do this is to look at this and say, all right, well, we've got a natural log here, we've got an x here. Remember that the natural log is the inverse function of the exponential. So natural log of e to the x is always equal to x, right? This is true for all x, all real numbers x. In particular, it applies to positive values of x, all right? So what we can do is we can make this replacement, right? Instead of leaving this as an x, we can replace it with this natural log of e to the x, and we can write our limit as the limit as x approaches infinity of natural log of e to the x minus the natural log of x. And then we can use a natural log rule here, right? So this is the quotient rule for natural logs, or any kind of logs, but this is the natural log here that we have. This becomes then the limit as x approaches infinity of the natural log of the quotient e to the x over x. And again, at this point, we can now use the continuity of the natural log. So what does it mean for a function to be continuous? Well, it means that that the limit commutes with the function. So the limit, when a function is continuous, the limit can go inside the function, right? So this log can be kind of moved to the outside in some sense. That is a property, that is the defining property of continuity. So we can do this because natural log is continuous. All right, so sometimes we get caught doing things like this and not remembering why we're allowed to do it, right? But in this case, we can do it because natural log is continuous. So what we end up with now is the natural log of the limit as x approaches infinity, e to the x over x. And this limit on the inside, we're going to focus on, and we'll just have to remember that it's got to go back into the natural log when we're done, right? So we're just going to focus on this now. The limit as x approaches infinity, e to the x over x. This is, of course, infinity over infinity. E to the infinity is very large infinity. This is obviously infinity. So L'Hopital applies, right? So at this point, we apply L'Hopital's rule. This becomes the limit as x approaches infinity. And we get the derivative, e to the x, right? Derivative of e to the x is itself. Derivative of x is just 1. And so when we plug in here, we get infinity over 1, and that is infinity. All right, so that means that the inside here approaches infinity. So what have we learned? Our original limit is now equal to this, whatever this means, right? So I'm going to put this in quotes, actually, because what this means is, actually, this is equal to the limit as x approaches infinity of ln of x, and that is, of course, equal to plus infinity as well, right? The natural log function, although when we draw the graph, it kind of looks like it levels off. It doesn't, right? It's always growing. It's just growing slowly. And so this is plus infinity. And so what we learn then for this limit is that as x approaches infinity, the limit is of x minus natural log of x is actually equal to infinity. That means that x is growing much faster than the natural log. The difference between them is infinite in the limit, right? In the limit. All right, but there's computation of another indeterminate form using L'Hopital's rule. And notice we had to remember some stuff about continuity here. Now, in the last example, I have one more for us. We're going to use a very similar approach here. We're going to introduce a natural log in, but let's first see why. So on this one, if we take the limit, what do we get? So we just plug in, right? Just distribute this limit out. If we were allowed to, what would it be? It would end up being something like 1 plus, as x goes to infinity, this whole thing goes to 0, very small. And then the exponent gets very large though, right? So this is something like 1 to the infinity, which would be 1 if this was truly 1, right? But the reason I wrote 0 plus here is because this is actually a little bit bigger than 1, right? This number is a little bit bigger than 1. And so multiplying a number that's a little bit bigger than 1 by itself infinitely many times, it's not clear what happens to that, right? 1 times itself infinitely many times is always 1. But if you just add something a little bit larger than 1, it's not clear. So this is actually indeterminate. Indeterminate. Because remember, in a limit, you never get where you're going, right? That's what I mean by this 1 plus and the 0 plus. They equal 0 and 1 in the limit, but you never get where you're going in the limit. So you can't just say it equals 1, right? So we need to do something to this. And what we can do is we can say, all right, let's suppose that this limit exists. And let's say, all right, if this limit exists, let's say that it equals L. All right, so it equals L. Now, we can take the natural log of this entire thing, right? So the natural log is a continuous function, as we just talked about. So we can apply the natural log to this equation, and I mean both sides of this equation. Natural log is 1-to-1, invertible, right? And so, by the way, this number 1 to a large power can't be negative, right? So it makes sense to assume that this L is probably a positive number. And we can apply the natural log. And so what we end up with then is that the natural log of our limit L, right, L on this side that we're looking for, is equal to the natural log of this limit, x approaches infinity, 1 plus 2 over x to the power x. And then we can do the same thing that we did on the last example, which is we can apply the continuity of the natural log to this limit, but we can do it in the opposite order now. We can use continuity to get the natural log inside of the limit, all right? And so what we end up with, after doing that, and again, this is by continuity. It's very important that we understand why we can do this, right? So by continuity, we can do this, and we end up then with the limit, x approaches infinity, of the natural log of 1 plus 2 over x to the power x, all right? But now we can use all the natural log rules that we want, right? And in particular, we can take the power rule and have this x come down in front, all right? And this is going to look very similar to our first example now, because we're going to end up with a limit as x approaches infinity of a product, x times the natural log of 1 plus 2 over x. And when we plug in this limit, what are we going to get? Well, x approaches infinity times log, this is going to be the natural log, right, of this limit is going to approach 1 plus 0. So it's going to approach 1. Natural log of 1 is 0. So this is an infinity times 0 again. So once again, that's indeterminate. This is the same case as the first example, and we're going to actually solve this the same way, okay? So when we apply this, we can, first of all, we have to rearrange it, right? So this is going to be the limit as x approaches infinity of, we can probably guess, we're going to do the same trick. Treat this as 1 over x, and then move it to the basement here. And this becomes the limit. Natural log 1 plus 2 over x over 1 over x. And now this one equals 0 over 0. Log of 1 over 1 over infinity. So 0 over 0, and we can apply L'Hopital to this. All right, when we do that, we end up with the limit x approaches infinity of derivative of natural log of u is u prime over u, right? So this is going to be 1 plus 2 over x prime, right? So what's that? Well, that's just going to be derivative of 1 is 0. So 2 over x prime over 1 plus 2 over x, all divided by 1 over x prime. So I'm going to do this the same way I did the last one. And then this derivative is linear, so this becomes the limit x approaches infinity, 2 times 1 over x prime. I just did this one previously, so I'm not going to explain every single step here, but 1 over x prime, times 1 plus 2 over x. All right, once again, if you trust my method here, this term and this term have to cancel, right? And what are we left with? So they're gone. And then the limit becomes, the limit as x approaches infinity of 2 over 1 plus 2 over x. That's 2 over 1 plus 0, or 2. All right, we feel like we're done. We finished the limit, right? But look, remember what we've got. The natural log of the limit that we wanted, right? The natural log of the limit we desire is equal to 2. So that's not the answer, right? That's not the answer to the original limit. The original limit, we have to undo this natural log, and that's done by taking the exponential, right? The natural exponential of both sides. And so we conclude that the limit as x approaches infinity of 1 plus 2 over x to the power x is equal to e squared, the natural number e squared. All right, so there's 3 examples of how to use L'Hopital's rule to compute indeterminate forms. They all have similarities, but at the same time, they're a little bit different. So make sure you understand all 3 of them. And I'll see you guys in the next video lecture.